I'm going to grade yours first, Ben. All right, so we're in 4.6, part 2. Graphing secant and cosecant. So I want to remember something about secant and cosecant functions first before we talk about the graphs. So if we have secant x, that equals 1 over cosine x. So they're reciprocals of each other. So if we're graphing y equals secant x, and it's this fraction, what happens when we graph functions with a fraction like this? What can happen? What do we have to be careful of when we're dealing with fractions like this? A 0 in the denominator. What happens to our graph when we have a 0 in the denominator? Think about what happened with the tangent function. An asymptote, a vertical asymptote. So we get a vertical asymptote when cosine x equals 0. So the graph of our secant function is going to have a vertical asymptote everywhere that the cosine function is 0. And the cosecant function, since it's 1 over sine x, we're going to get a vertical asymptote everywhere that the sine function is 0. And what it turns out is that the secant and the cosecant, the graph of our sine function and cosine function are really the key. So since we already know how to graph sines and cosines with shifts and stretches and all that kind of thing, graphing secants and cosecants is going to be real easy. So I'm going to say we're just going to do this all at once because it's the same for both. So to graph y equals a secant bx minus c plus d, or y equals a cosecant bx minus c plus d. The first thing we're going to do is graph the parent function. So the parent function of a secant bx minus c plus d is a cosine bx minus c plus d. Parent function of the cosecant, a sine bx minus c plus d. We already know how to do that. That's really 90% of our graph. Graph the parent function. 2. From what we just talked about here, we're going to sketch asymptotes everywhere the parent function is 0. And on our graph, where the parent function equals 0 is everywhere it crosses the x-axis. So wherever our parent function is crossing the x-axis, we get an asymptote. Nice and easy to do. This next part sounds a little confusing, but it's not. The function has a minimum at each maximum of the parent. I'm just going to write max. And so what that means is on the top of each curve of our sine or cosine, we get a point that's on our secant or cosecant function. And then we're going to turn that around. We're going to look at the bottom part. So our function has a maximum at each minimum. And I'm just going to write min. of the parent. So that means at the bottom of all of our sine and cosine curves, we're going to get a point on our secant or cosecant. And then to sketch our graph, all we have to do is connect that point, and we sketch our graph kind of a parabola shape between the asymptotes. And once we do an example, what we've said here in words will make a lot of sense. It's really, really easy. So we graph our parent function, which we already know how to do. Put our asymptotes everywhere our parent function is crossing the x-axis. That's where our parent function equals 0. From the top of each of the curves, we sketch between our asymptotes, and from the bottom of each of our sine or cosine curves, we sketch between our asymptotes. All right, questions on what we've written here? So all I want to do is just a couple of examples of sketching. We'll do a secant and we'll do a cosecant function. So let's graph. We'll make our parent functions easy because we know how to graph the parent function, so we don't need to make it really complicated. 2 cosecant x over 2. So our parent function, what we're going to sketch is y equals 2 sine x over 2. So we know our amplitude equals 2. Our period equals 2 pi over 1/2, or 4 pi. And we get key points every pi units. Now we're ready to draw our graph. So I'm going to graph, let's see, every pi units, pi, 2 pi, this is nice and easy, 3 pi, 4 pi, look at all these pi's in this class, minus pi, 2 pi, negative 3 pi, negative 4 pi. All right, and we're graphing a sine function. I'm going to do label my y-axis, so I go from positive 2 to negative 2. We're not shifting at all, so our sine function starts at 0 here, and we get points at all of our key points here. Go this way. So this is a problem we already know how to solve, so we're climbing up that second coconut tree. So there's my parent function. I sketch an asymptote everywhere the parent function equals 0. So everywhere it crosses the x-axis, we'll get a vertical asymptote. And then we get a point on our graph at the top and the bottom. And then we sketch kind of a parabola shape between our asymptotes. And I'm just putting little arrows to remind us. It doesn't stop, it keeps going. And the blue, what we sketched in blue there, is our cosecant function. Some people like when they sketch them to kind of erase the parent function. You don't have to. You can leave it just like that, and that would be fine for your sketch. We graph our parent function, and then just graph our little kind of sort of parabola shapes. They're not exactly parabola shapes, but they look a little like parabolas between our asymptotes. And we're done. That's all there is to that one. So graphing the parent function is really 90% or more of what we have to do. All right, questions there? Yes?
We already conditioned ours with the parent function would look like we go on the drive when we just get into the
Yeah, as long as you know what if your mental picture of the parent function is okay, and as long as you're labeling your points, so if you know this is at pi and your asymptote is at 2 pi, so as long as you sketch everything in there in the right place, you're fine. Okay. All right, let's look at one more. Let's do a secant function. So we'll do y equals secant x plus pi. So our parent function, y equals cosine x plus pi. So we're all set on this one, really. All we're doing here is shifting left by pi. Our period's 2 pi. We still get key points every pi over 2 units, every quarter of a period. So we can sketch our graph. So I'm going to go by, label my x-axis by pi over 2 units. And I'm going to go in the negative direction. And we're shifting left by pi units. So I'm going to start my cosine graph over here, and we're going up. Our amplitude is 1, so we'll go up, down 1. So I'm starting over here at pi rather than at 0. And I'm just going to sketch a point at all of my key points there. And then I'm going to put an asymptote everywhere my parent function 0, everywhere it crosses the x-axis. And then I get a point on my graph here, go up, make this kind of parabola shape. And the graph in blue would be my secant function, secant of pi, or x plus pi. And that's it. So once we graph our parent function, we're pretty much done. Yes?
Is there a specific way you have to graph the parabola function?
No. I mean, to be more accurate than we are would take a lot more work. So just roughly a parabola shape is fine. Yeah.
Why is the cosine graph function starting at -1 instead of
Because it's shifted left by pi. So I actually started my graph here. So shifting left by pi is the same as a reflection over the x-axis. Kind of interesting relationship there. All right, questions there? All right, yes.
So if there's not an asymptote on the outside, you still like draw this?
You could draw this. The only reason I didn't draw it is because I don't have the asymptote there, so
Okay.
I just drew it towards a 1. But yeah, this is fine, and you'll often see them sketched like in a book or something. It'll look like that. Yeah. So if you graph 2 periods, normally I ask for 2 periods. So if you graph 2 periods of the parent function, and then just graph the other ones based on those 2 periods. Okay. Other questions? Okay. If you're copying the homework from the board, the problems in parentheses skip. I decided not to do that stuff today. There you go.